Dear students, Assalamu alaikum. Today I will be covering your second experiment for your DLD lab session, and its title is Implementation of Boolean Expressions through Logic Gates and also Verification of Demorgan's Law. This is going to be a bit lengthy task for you this time, but however, you will learn through this the intermixing and usage of connecting different types of ICs to implement any Boolean expression. So let's see how does this work. Components you will be requiring are for this particular lab are 7408, 7432 and 7404 ICs, and you will be requiring a virtual breadboard which is available in your NI Multisim, and the versions that I have preferred for you to use are from 13.0 and upward and onwards. So before I give you an overview in the slides, I will try to explain your tasks in detail on this whiteboard. Now, what are basically Boolean expressions? As you have already learned in your previous courses about Boolean algebra, we know that any kind of Boolean expression that are represented in the form of Boolean algebra are basically representing some kind of logical operations that are being performed on any kind of inputs. So we are representing the inputs in the form of variables, and the logical operations which are to be performed between those variables are to be represented in the form of mathematical symbols. And however, the Boolean algebra is not exactly the same as that of the mathematical algebra or the linear algebra that you have studied in your mathematics. There are some kind of differences because the logical operations do not necessarily give you the same answers as that of your linear algebra. I'm going to implement, I'm going to start through the first example that I've also already presented in your slides as well. The first example is a Boolean expression given like this: f1 is equal to x plus y complement z. Now, according to Boolean algebra, um, we have three input variables representing this whole expressions, and there is one output variable, that is f1. The input variables are x, y, and z, and there are some logical operations being performed between these input variables. That is, one of the operator is plus. This operation is equivalent to and, sorry, not and, this is equivalent to or logical operation. Similarly, we have another operation, that is complement, and this is equivalent to not logical operation. And we have another operation being performed here, which is the dot operation. This is the dot operation, and this is equivalent to and logical operation. And in your previous lab, you have already gone through the truth tables of all of these three logical operations, so I'm sure that this will not be difficult for you to understand. Now, how to verify or to find out that what is going to be the output f1 in case we have three different input variables and all of these variables have at least 8 different combinations. So the procedure to find out is to derive a truth table. We are going to derive a truth table for this. This is only a revision of what you have already studied before. Your expression is here f1 equals x plus y complement z. Right. So let's start through the truth table. The truth table is on the left hand side. We conventionally uh, input put down the inputs here x, y, and z. And since we have three different input variables, so we have 2 raised to power 3 equals 8 different combinations of these variables. These will be 0, 0, 1, sorry, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and last one, 1, 1, 1. Right. Now, for your ease, for the first time since you are trying to implement this, I will perform each of these three uh, logical operations that I have mentioned. First, I will implement the NOT operation, which is y complement. Right. So, by convention, we always first perform the NOT operations. This is actually a sum of product representation of this Boolean expression. So in case of a sum of product kind of representation of any Boolean expression, we first implement the logical NOT operation, right? And after that, we perform the logical AND operation, and in the end, we perform the logical OR operation, right? So first I'm going to complement Y. Whatever is present in Y is going to be complemented here. First we have 0, 1, it becomes 1, and 0 becomes 1, 1 becomes 0, 1 becomes 0, 0 becomes 1, 1, 0, 0, right? And the next case is the logical AND operation, right? And this is happening between Y complement and Z. So this and this are going to be AND here. So this is this will be having a same truth table in which um, only one combination gives you an output 1, otherwise in all cases we have 0. So when we have 0 and 1, 0 dot 1 or 0 and 1, we get 0. 1 and 1, we get 1. 0 and 0 get 0. 1 and 0 get 0. 0. 1, 1 gets 1. 0 and 0, right? And in the end, we are going to get f1 equals x plus y complement z. So we already have y complement z, and now we are trying to OR this y complement z with this x. So in OR case, only 0 and 0 combination gives an output 0, otherwise for all other cases we have 1. So in the first case we have 0 and 0. 0 ORed with 0 or 0 plus 0 gives 0. 0 and 1 gives 1. 0 and 0 gives 0. 0 and 0 gives 0. 1 and 0 gives 1. 1, 1 gives 1. And 1, 1, 1, 0 gives 1. And 1, 0 gives 1. So this is my final output that is going to be received once we have all of these 8 input combinations of x, y, and z. Now how do we actually, now the first step, I have already gone through the first step, that was by seeing the Boolean expression, we can derive a truth table, right? And after that, the next step is that we have this truth table and we are going to verify this truth table using a circuit diagram. So our equation was like this: f1 equals x plus y complement z. So as I said, that in the case of SOPs, that is sum of product form, we are first going to implement the complement thing. So we are trying to draw a circuit diagram or a logic circuit diagram from this expression. The first thing is we are going to get x, y, and z input. We have already separated out the inputs. The first thing is we are going to not y. We get y not here or y complement here. And after that, we AND it with z. So we draw an AND gate, and at the output of this AND gate we get y complement dot z, right? And after that we are going to OR this y complement z with x, right? So this is going to be my f1, which is equal to what? X plus y complement dot z. Now the question is that if I'm asking you that you are going to implement this circuit diagram in Multisim, what does this mean? This means that you are going to utilize ICs for this purpose. What does this mean? I am going to have 3 different ICs because I have 3 different operations, and I am requiring what? I am requiring one NOT gate, one AND gate, and one OR gate. Although in each IC we have four number of gates for each uh, four number of gates for each of these NOT, AND, or OR gate, but however we are going to utilize only one of those to implement this circuit. So I'm going to draw the first IC, that is my NOT IC 77404. It has 7 pins on the bottom side, 4, 5, 6, 7, right? This is going to be my ground, and 7 pins on the other side, 5, 6, 7, right? And this is going to be my VCC. Now in the input we have a structure like this. At pin number 1 I have the input of first NOT gate, and at pin number 2 I have the output. Since I am going to use only one NOT gate here, only one, so this means that I can use either this gate or at pin number 3, 4, either this gate or any other gate you wish to use. There are actually 6 NOT gates in this whole IC. You can utilize any one of those. So another IC I'm going to utilize is AND gate IC. It has a similar structure, but however it has only 4 gates. 1, 2, 3, 4, 5, 6, 7. This is ground. And 1, 2, 3, 4, 5, 6, 7. This is VCC 7408. And another IC is that we are requiring is 7432, which is my OR IC. It has again the same structure as that of 7408. 1, 2, 3, 4, 5, 6, 7. This is ground. 1, 2, 3, 4, 5, 6, 7. This is VCC. I have internal structure like this, and it has an internal structure like this. And since I'm going to utilize only one of all of these gates, so I'm only representing here a single gate. Now how do I interconnect these in the form of this circuit? I'm going to implement this circuit right here. This is the circuit that I'm going to implement. Now how do I do this? The first thing was that I am going to separate out my interactive digital constants, which are my inputs x, y, and z. These are x, y, and z. Now my first objective was that I need a complement of y. So for this purpose, what I do is that I input y at pin number 1 of NOT gate IC, that is 7404. So what will appear on pin number 2? That will be Y complement, because this NOT gate is automatically converting it into a complementary form. So whatever you are applying at pin number 1, that is Y, either it is logic 0 or logic 1, it doesn't matter. You are applying an interactive digital constant or a switch value or a variable value to pin number 1 of the NOT gate IC, and pin number 2 will automatically calculate its complement. Now what I'm going to do is the next step. The next step was from this circuit diagram. This was that I am applying this complement, Y complement, to an AND gate's input. And another input of this AND gate is going to be Z. So let's see how I'm going to do this. I am going to take a wire from this pin number 2 and apply at the input pin number 1 of this AND gate IC. And I'm going to take a wire from here, from Z, right? And I'm going to apply it at pin number 2 of this AND gate IC. Right, so both of the inputs are completed. Now what will my pin number 3 produce? Pin number 3 will produce whatever were present at the input. They will be ANDed, or they will be dotted together. So what will appear at pin number 3? That will be Y complement dot Z. I have provided Y complement at pin number 1 and I have provided Z at pin number 2. So my pin number 3 will present, automatically it will present Y complement dot Z. Why? Because this is an AND gate IC. Whatever we are providing at pins 1 and 2, they both will be automatically ANDed together. Now I have received this part of your expression, that is f1 equals x plus y complement z. I have received this part of my expression. What I need to do is to OR this part of my expression with x. Now for that purpose I will require an OR gate IC. What I will do here is that I take a wire from pin number 3, which already has y complement dot z, and attach it at pin number 1 of this OR gate IC, right? Now the second input of this OR gate IC is still empty. Now my expression says that the second input should be x. So I take a wire from x and apply it at pin number 2, and what pin number 3 will give me? Pin number 3 will automatically give me an OR of both x. Now it has what pin number 1 में क्या आ रहा था? That was x complement, sorry, y complement dot z, and पिन नंबर 2 में आ रहा था x. तो मेरे पिन नंबर 3 में ऑटोमेटिकली क्या आ जाएगा? x plus y complement z. So this is going to be my final output because I don't need any further Boolean algebra or any logical operations further to be performed on this output. This is supposed to be equivalent to my left hand side. So to observe this output, I am going to attach this output to an LED. Now LED की वर्किंग ऑब्जर्व करने के लिए हमें कैसे पता चलेगा कि हमने ये सर्किट जो इम्प्लीमेंट किया है ये ठीक किया है या गलत किया है? तो उसके लिए मैं क्या करूँगी कि इस LED की ऑन एंड ऑफ की जो सिचुएशन है उसको ऑब्जर्व करूँगी. उस ऑब्जर्व करने के लिए मैं अपना ट्रुथ टेबल सामने रखती हूँ. This is my truth table. This here, right? So I am going to apply 0, 0, 0 at all of the interactive digital constants or the input switches that are X, Y, and Z. I'm going to apply 0, 0, 0 at all three of them. So my LED should not glow. That means my output is going to be off. For to check again, I will apply the second combination, that is I will keep 0, 0 at X and Y, and I will um, change the logical value of Z to 1, and then I should observe that my LED should glow because my second combination is 1. Similarly, all of these combinations are going to be in correspondence with my circuit that I have implemented. Let's try this in my Multisim. I am going to use 3 ICs here, TTL, and I'm going to use NOT gate IC, right, and I'm going to use AND gate IC, and I'm going to use OR gate IC 7432. Sorry. Right. Now I need at least 3 inputs. So I'm going to go to sources, digital sources, interactive digital constants. I need at least 3 inputs, X, Y, and Z. I will name them as X, Y, and Z. And I also require VCC and ground to keep these ICs in operative mode. And I'm going to use only one VCC, and I will interconnect all of these ICs with the same VCC and ground. And after that I have one single output, so I will require only one LED or a single indicator probe. And now I'm going to close this. First I will connect all of these with the ground. This is going to be my ground. This is going to be my third ground, and after that I apply VCC here, and then I apply VCC here and another VCC here. Now this is going to be my X, so I relabel it as X. This is going to be my Y, so I'll relabel it as Y, and this is going to be Z. According to my implementation, first Y is going to be complemented, so I apply it here, and then I AND it with Z. So I take the output from this and then I apply it to AND gate's first input. This is exactly what I just suggested you, y complement dot z, and then I take this as the output, and then I OR it with x, and at 1y I get my final output. This is my x1, sorry, f1. So let's see, at 0 0 0, there is some minor problem. By complement dot, anyways, oh sorry, right, I accidentally placed a wrong value here. 74, not 132, I should have placed 7432, right? I'm going to replace it. So now I try again. Now it's working fine, and when I place 1 here, now it's going to glow, right? So this is exactly according to my truth table, and now I will actually verify it um, using my truth table. So what's your task? You have understood till now that how you are going to implement a given Boolean expression in the form of a logical uh, circuit, and how you are going to implement it using ICs. Um, this is exactly what I explained to you on your whiteboard. So what is your first task? Your first task is that I have presented here a Boolean expression which is f2 x complement y complement z plus x complement y complement z plus x dot y complement. So there are basically here I have a dot operation, another dot operation, dot and dot and dot. So I need at least how many AND gates? 1, 2, 3, 4, 5. I need at least 5 AND gates. So for this purpose, I will utilize two AND gate ICs. Two AND ICs, right? And how many OR gate ICs OR gates I require? I require at least two. Since I have two plus symbols here, plus symbols are only two here, so I need two OR gates. So I will only need one OR gate IC. Why two AND gate ICs? Because in one IC we have only 4 gates. So to implement the fifth gate, we will require another AND gate IC, right? And how many NOT applications or NOT logical operations are being implemented here? X is being complemented, Y is also being complemented, Z is not being complemented. So I need only two NOT gates. So I will need only one NOT gate IC, because in one NOT gate IC we have 6 gates and we can easily utilize 2 of them. So my suggestion is that you try this on your own, and we will discuss about your problems, whatever problems that you face using your multisim, and you will be requiring only ICs to implement this circuit. So you try to derive its truth table. First you draw its truth table, and then you draw the circuit diagram, and through that circuit diagram you are going to implement this Boolean expression on your multisim. So this is your task 1. Now your second task. The second task is a bit tricky. It is very easy but a bit tricky. So I will try to explain this in an easy way on your breadboard, on your whiteboard. This is Demorgan's law. Demorgan's law has two laws. This theorem has actually two laws. One of the laws states that if we have two variables in the form, it is only represented in the form of two variables. Either we can represent it in the form of x or y or a or b, and or whatever variables you wish to utilize. We have two variables x and y, and there is an OR operation being performed between both of these. But however, if we try to implement another operation on both of these all together, that is a NOT operation. If we try to complement OR of x and y all together, then this should be De Morgan's theorem states that this should be equivalent to x complement dot y complement, right? Now the second law states if we have x complement plus x dot y whole complement. If now this time we have an AND operation being performed between both of these variables x and y, and now I'm again trying to complement it on the whole. Now this law states that this is equivalent to x complement plus y complement. Now what De Morgan theorem actually tries to tell you that if we are applying a whole complement on the left hand side of the equation, then on the right hand side everything becomes complemented. All the logical operations becomes complemented. X is complemented, y is complemented, and also or this or is also complemented. This or becomes AND operation on the right hand side. So what this law tries to tell you is both the left hand side and right hand side should be equivalent. If you try to implement the left hand side and then you also try to implement the right hand side, your answer in both cases will be the same. इसको चेक करने का क्या तरीका है? सिमिलरली मैंने अब जो सेकंड लॉ स्टेट किया उसके अंदर भी एग्जैक्टली ऐसे ही है कि जब हमने होल कॉम्प्लीमेंट ऑपरेशन परफॉर्म किया तो आपका एंड ऑपरेशन जो है इट बिकम्स और ऑपरेशन, और एक्स और वाई बोथ वेरिएबल बिकम कॉम्प्लीमेंटेड. तो इसको चेक करने का तरीका ये है कि हम लेट सपोज फर्स्ट लॉ, अभी हम फर्स्ट लॉ को वेरीफाई कर रहे हैं, ठीक है? तो उसके लिए मैंने क्या किया कि मैं लेफ्ट हैंड साइड और राइट हैंड साइड बोथ को इम्प्लीमेंट करती हूँ यूजिंग द सेम सर्किट. तो लेफ्ट हैंड साइड के अंदर एक और ऑपरेशन हो रहा है और एक नॉट ऑपरेशन हो रहा है. तो मुझे और नॉट दोनों की आईसीस चाहिए, बट राइट हैंड साइड के ऊपर एंड ऑपरेशन भी हो रहा है अलॉन्ग विद नॉट. तो उसके लिए मुझे एक एंड की आईसी भी चाहिए होगी. सो आई नीड अगेन ऑल ऑफ दीज आईसीस. एंड व्हाट आर दोज? This is my first IC. Seven 7404. This is my NOT. 7408. This is my AND, and this is 7432. Or 1 2 3 4 5 6 7. This is understood that 7 and 14 are going to be ground and VCC respectively. So I'm going to use X and Y here. since I have only two variables, my left hand side was x plus y whole complement, right? So I'm going to implement x and y. First I'm going to implement the left hand side. तो उसके लिए मैं क्या करती हूँ कि मैं x अप्लाई करती हूँ यहाँ पर, सॉरी नॉट हियर, x को मैं अप्लाई करती हूँ और में 4 5 6 7 1 2 3 4 5 6 7, x को मैंने अप्लाई किया और में, y को भी अप्लाई किया और की सेकेंड इनपुट पे, तो सेकेंड यहाँ पर क्या आ गया x प्लस वाई। अब मुझे इसका होल कॉम्प्लीमेंट भी करना है, तो मैं यहाँ से एक वायर लेकर इसी को कनेक्ट कर देती हूँ यहाँ पर। तो ये क्या आ गया मेरे पास x प्लस वाई का होल कॉम्प्लीमेंट। इसको मैं अप्लाई कर देती हूँ LED 1 में। एक मैं, चूँकि मैं लेफ्ट हैंड साइड को भी ऑब्जर्व करना चाह रही हूँ और राइट हैंड साइड को भी ऑब्जर्व करना चाह रही हूँ, तो दोनों की ऑब्जर्वेशन के लिए मैं अलग अलग LED लेती हूँ, राइट। अब राइट हैंड साइड मेरी क्या है, राइट हैंड साइड इज इक्वल टू एक्स कॉम्प्लीमेंट प्लस वाई डॉट वाई कॉम्प्लीमेंट। तो मुझे सबसे पहले क्या चाहिए, एक्स कॉम्प्लीमेंट। मैं सेकंड गेट पे जाती हूँ, let me use another color for this. I'm going to utilize second gate. This is my second gate, right? और यहाँ पर क्या आ जाएगा x complement. This is x complement. मैं यहाँ से एक वायर लेकर एंड गेट की फर्स्ट इनपुट पर अप्लाई करती हूँ। क्यों? क्योंकि मुझे एंड ऑपरेशन करना है x कॉम्प्लीमेंट का y कॉम्प्लीमेंट के साथ। तो अभी मेरे पास x कॉम्प्लीमेंट तो आ गया, y कॉम्प्लीमेंट रह गया। तो y कॉम्प्लीमेंट को मैं थर्ड गेट में अप्लाई करती हूँ। दिस इज माई थर्ड गेट बिटवीन पिन नंबर 5 एंड 6। तो 6 पिन पे मेरा y कॉम्प्लीमेंट आ गया। इसको मैंने, लेट मी यूज़ अनदर कलर फॉर दिस। दिस इज माई, मैंने पिन नंबर 6 से y कॉम्प्लीमेंट लिया और y कॉम्प्लीमेंट को मैंने इस एंड गेट की सेकेंड इनपुट बना दिया। सो फर्स्ट इनपुट पे क्या आ रहा है x कॉम्प्लीमेंट और सेकेंड इनपुट पे आ रहा है y कॉम्प्लीमेंट, और थर्ड इन आउटपुट पे क्या आ रहा होगा, ऑब्वियसली दिस जो भी ऑटोमेटिकली ये इसको एंड ऑपरेशन परफॉर्म कर रहा है, तो x कॉम्प्लीमेंट डॉट y कॉम्प्लीमेंट आ रहा होगा। सो दिस इज माई राइट हैंड साइड। इसको मैं अप्लाई कर देती हूँ LED 2 में। LED 2 में अप्लाई कर दिया। नाउ मैं x और y, मैंने अब एक्चुअली दो सर्किट्स इम्प्लीमेंट किए, एक लेफ्ट हैंड साइड और एक राइट हैंड साइड, और उन दोनों को इम्प्लीमेंट करके मैंने दो डिफरेंट LEDs में लगा दिया उनकी आउटपुट्स को। तो अब मुझे ये कैसे वेरीफाई होगा कि मेरी लेफ्ट हैंड साइड इज़ इक्वल टू राइट हैंड साइड? वो इस तरह से वेरीफाई होगा कि आप इनपुट का कॉम्बिनेशन जो भी रख रहे हो, 0 0 रख रहे हो, 0 1 रख रहे हो, 1 0 या 1 1, तो इन any of these four cases your LEDs, both of the LEDs should glow or remain off at the same time. अगर किसी कॉम्बिनेशन पर 0 आ रहा है तो दोनों LEDs का 0 होना चाहिए, और अगर किसी कॉम्बिनेशन पर 1 आ रहा है तो दोनों LEDs का 1 होना, ग्लो होना ज़रूरी है। उसके लिए आप उसका ट्रुथ टेबल बना लें। लेफ्ट हैंड साइड और राइट हैंड साइड का ट्रुथ टेबल सेम ही आएगा। तो आप ट्रुथ टेबल बनाकर उसको वेरीफाई कर सकते हैं कि कौन से कॉम्बिनेशन के ऊपर LEDs को ग्लो करना चाहिए और कौन से कॉम्बिनेशन के ऊपर LEDs को ऑफ रहना चाहिए। ये आपने सेकेंड लॉ को भी एग्जैक्टली इसी तरह वेरीफाई करना है। सो आई होप दैट दिस थिंग इज क्लियर टू यू, and I'm not going to explain it on Multisim, and I'm expecting that you are going to work this out on your own. This is your second task. You are going to um, implement both of these theorems, and then prepare a lab report and then submit me by next Thursday, inshallah. And we will discuss about your problems on Friday, on coming Friday, inshallah. I hope that today's lecture is a bit lengthy but easier for you to understand. We will discuss in your next lab. Allah Hafiz.